are going to start the lecture on advanced reaction engineering. So, today we will discuss about the design equation for continuous reactors that we have studied in our previous class. So, today I will discuss the sizing of that particular continuous reactor. So, continuous start tank reactor, flux flow reactors, packed bed reactors. So, sizing or volume or weight of the catalyst that we will discuss from the design equations. And let us start the conversions and reactor sizing. So, we have already discussed about the general mole balance and for a particular reactors or commonly used various industrial reactors that we have discussed, and during the sizing or volume determinations. So, before that we know that the reactions we have to conduct any reactions. So, let us say the general equations or general reactions that usually expressed for chemical engineering, that we said that A plus B going to C plus D, and small a, small b, small c, small d, these are the coefficient. Okay. So, stoichiometric coefficient. So, this is the general equations reactions and different type of reactors and their design equations we already have discussed. So, the reactions there are many type of reactions, that may be reversible reactions, irreversible reactions. So, when a reaction is reversible reactions, then we can maximum the conversion that we can achieve for that particular reaction, that is the equilibrium conversions for that particular reactions if we conduct in our any reactors. So, and for irreversible reactions 100% conversion, that is the possible theoretically. So, for that particular reactions that is possible. So, okay. So, these are the things we need to know before start that. And here for batch reactors, we said there is no inflow, there is no outflow for the system. So, whenever the concentrations of that component reactants we express, that is in terms of Na or Na naught, Na that is the number of moles after T times, Na 0 that is the moles reactant that is present inside of the reactors, or this way means Na naught that is the number of moles of A initially present in the reactors, and Na that is the moles of A that is left inside of the reactor after reactions, and Na 0 x that is the amount of the reactant A that is being consumed or reacted during the reactions inside of the reactor. So, this way moles of amount reacted that we can express moles of A that is charged, and conversions if you know, that way amount of the A that is reacted during reaction that we can express that way. Okay. So, these are the basic things we should know, means therefore, we are I think you know still we are also discussing to. So, here conversions X that we can express in terms of moles of A reacted and Na 0, that is the amount of the moles that is charged at the beginning for the batch reactors. Okay. So, then we can write Na equals to Na naught minus Na naught into X. So, that amount of the A remain inside of the reactors, or we can write Na 0 equals to 1 minus X. This way we can write this number of moles for the amount of component A present in the reactors. Okay. So, the batch reactor design equations already have discussed for differential form that we have expressed. So, in this differential form of design equations, if we integrate this with respect to the t equal to time 0 to x when initial means just reactant have been charged or charged inside of the reactors, then conversion would be 0, and at time t the conversions would be x a. Okay. So, within that this design equation, after rearranging this we can get this, and then if we integrate this 0 to t time and 0 to x a. So, finally, the integrating form of design equations will get for the batch reactors that we have discussed. And now, the for flow reactor design equations similarly, means whatever the these forms means number of moles present here in terms of moles. So, when batch reactor is there, so we express always mole initial to mole present final. Okay. This is t equal to 0 and t equal to t means whenever initial or finals we consider in terms of moles, since there is no flow, time units would not come. means total elapsed time or total time is required to convert all reactant into product, that we can measure using these equations. The total time is required to convert, let us say 0 to let us say 80% conversions of the desired product. So, then how much times that usually we can calculate using this design equation. But when flow reactor is coming, I said flow means molar flow, okay, molar flow that is coming. So, in that case by either batch reactor, CSTR or PFR or packed bed reactors or any kind of reactor. So, flow reactant components in the terms of flow, then so we always express in terms of moles per unit time, okay. That way we should express. So, here Fa naught Fa, that is the molar flow rates, molar flow rate Fa naught, that is the entering A component A, and Fa, that is the molar flow rates of A leaving from the system, and Fa naught into Xa, that is the amount of the A that is consumed or reacting per unit times. So, Fa equals to, that is coming out, easily we can find out using Fa equals to Fa naught minus Fa naught. So, Fa we can write Fa naught into 1 minus x this way, okay. So, this way or either way we can write. So, now the systems we express in terms of molar flow rates. So, here the reactions in plug flow reactors, CSTRs or packed bed reactors, we can the reactants we can charge that may be in the form of gas or in the form of liquids. So, when it is in the form of liquid, then concentration how will express, okay. So, concentration Ca naught, that way we can use. So, concentrations mole per dmq. So, if we know concentration of Ca naughts of that particular component, molar flow rate or volumetric flow rate V naught, if we know, then Fa naught we can calculate, or that out or exit stream is there. So, that for that stream Fa we can calculate, Fa equals to Ca into V volumetric flow rate. So, if we concentration know, the means reactor is like this flow reactor. So, here's reactant will enters, here product will come, here component A concentration high, here concentration of A would be low, means this is inlet concentrations and this is outlet concentration. So, this outlet concentration if you know, so then concentration of A is known, so volumetric flow rate is known. So, then if volumetric flow rate is known, so then molar flow rates we can calculate, mole per unit times we can calculate. So, for in case of the gaseous system, so gas to get the concentrations we know the inlet and outlet pressure, partial pressure. If pure component is there, that is fine. If with that some other also carrier gas, carrier component would be there, that would be mixed up with that reactants, then partial pressure mole fractions would come. So, then the concentration of in that case is we can express in terms of Ca naught equals to Pa naught by R T naught equals to Ya naught P naught by R T naught. So, here Pa naught, that is the partial pressures, that is the mole fraction, and this is the total pressure at the beginning, okay. So, here inlet temperature entering total pressures that we know. So, here gas constant and temperature if we know, the initial concentrations we can find out, okay. So, here once know the initial concentrations, then we know the volumetric flow rate. So, then this way initial molar flow rates of Fa naught if the systems is gaseous system. So, this way we can calculate concentrations, molar flow rate, how they are interrelated, volumetric flow rate, pressure, mole fractions, okay. So, these are the things, few things we need to know, therefore, we are discussing. So, now we know these are the things CSTR reactors, design equation for plug flow reactors that we have discussed, and design equation for packed bed reactors that we have discussed or we have derived. So, these are the three equation for flow system or continuous reactors we have. So, now we have to conduct the reactions, the specified reactions. Here we are going to study the reactor volume determinations or weight of the catalyst that is required for a particular or specified conversions that we are going to calculate, means measured, means volume or weight calculation measurements we are going to do. So, then we need to know once we start any reactions from the laboratory scale to the lab scale or industrial scale pilot plant reactor if you want to design, then before that you have to conduct the lab scale reactions. The same reactions we have to conduct in the lab, and in the lab scale we have to means develop this type of data, means rate versus conversions. means if we get let us say 10% conversions, 20% conversion, 30% conversion, 50% conversion if you want to get for this particular reaction, then what would be the rate, corresponding rate, that we should know. Means this rate versus conversions, that data we should know to find out the volume. Okay. So, if it is let us say first order reactions, if we assume the reaction is first order, we should know, means rate constant, initial concentrations, and by that way using these equations, if this particular reaction is let us say first order, then rate constant you should know, initial concentration you should know, just vary x, then corresponding rate will get. So, these tables will get, or we can develop this. Okay. Now, this laboratory data we can implement or use. Now, if we choose let us say CSTR reactors, there if we conduct these reactions, then what would be the volume of the reactor. Same reactions if we conduct plug flow reactors, then what would be the volume of the reactor, same data we can use. Okay. And if we use packed bed reactors to carry out these reactions, then how much amount of the catalyst is required to get these desired conversions, that easily we can find out. So, these are the design equations we have, and this laboratory data we have. So, here I said these are the data we will get from the laboratory, and thence we can plot rate versus 1 by minus R A versus conversions, we can plot 0 to 1. Okay. Maximum conversions would be 1. So, up to this we can plots 1 by minus R A. So, for this is for plug flow reactor. So, here this type of lines at we can get. Okay. So, this is the rate versus conversions data from these tables we have plotted this, is in the form of graph. Okay. So, now, so if we look into this, so here rate would be very high and here rate would be very low, since here at the beginning when conversion was very low, on that time concentration of the reactant was very high. See here concentration of the reactant, this is the concentration of the reactant, this is was very high, then rate would be very high, and at the beginning end of the reaction. So, their concentration of the reactant would be very low, since gradually reactant consuming concentration of that reactants remains very low, then at this particular point rate would be very low. Okay. So, now if we conduct that same reactions in a plug flow reactor and a CSTR reactors, then how does it look like. So, this is the design equation for CSTR reactors. So, in the left hand side volume is there, right hand side Fa naught by minus R A and x is there. So, in Fa naught by minus R A, if we plot y axis, and in x axis we are conversions, means from the data or tables we already have this data. So, from this data if we plot, it would be look like this, means for CSTR reactors means Fa naught by minus R A and x A conversion data we can plot, so we will get this, and then let us say we need a 80% conversions, though then we can draw this line and we can get this. This is the total volume of the CSTRs, the shaded area. This shaded area would be the total volume for the CSTR reactor for let us say 80% conversion. If you want to get 60% conversions, so then only let us say this is up to this is 60%. So, then this would be the total volume for 60% conversions, x equal to 60.6 for that we need to this shaded area. So, this way we can graphically we can find out what would be the reactor volume, the shaded area. So, that way using the design equations and the rate and conversion data we can find out this. Similarly, for plug flow reactors, if we conduct the same reaction, similarly we will get this data Fa naught by minus R A and conversion data. So, here in case of the plug flow reactors only the shaded zone or is this one. Okay. So, this part we have to measure, this part, this shaded area, this would be the volume of the reactor in case of the plug flow reactors, but in case of the CSTR reactor easily you can find out, means you know up to this distance, if you multiply, and then the total area will get. So, that way you can find out the total volume is required to carry out that reaction for a specified conversions. Okay. So, here the design equations for the same reactions if you conduct in a plug flow reactors, here the concentration area will be this area, and by this way the total amount or volume is required, so we can find out. So, now if we compare the same reactions we are carrying out plug flow reactors and CSTR. So, here CSTR reactors that much volume is required, and for plug flow reactors that volume is required. So, if you compare both, so here see both, if you are these two we are plotting in the same graph. So, here see these are the part, or this part is the excess area, means excess volume is required for a CSTR reactor. So, see the for the same conversions, if you want to get, here conversion is 80% conversions. Okay. For that reactions, let us say this is going to this, for this particular reaction, if you want to get 80% conversions, then CSTR reactors the volume always will be a larger amount, a larger volume is required as compared to the plug flow reactor to get the same conversions. So, then of course, we will choose for plug flow reactor since their volume is required smaller. So, this is the means difference in between plug flow reactor and CSTR reactors to get a specified conversions. In this particular CSTR reactors required larger volume to get the same conversions. Okay. So, now there is some numerical technique is there, means in case of the CSTR reactor easily we can means find out this area under the curves and to find out the volume. But in case of the PFR reactors, so area within these curves how we can measure. So, easily it is not easy to find out individual points and to get the accurate area under this curve. So, therefore, there are some numerical techniques are there which are called trapezoid, Simpson's rules, Simpson's 1/3 rules, here 2 points rule, 3 points, 4 points rules is there. So, this integration part means right hand side integrations that we can do using this one particular means Simpson's 1/3 rules or Simpson's 3/8 rules, 4 point rules, anyone we can choose, and this integrating part we can find out, we can put it here, then that would be corresponding volume at this specified conversion. So, just trapezoid rule is there, let us say two different points are there, this is x0, this is x1, 2 points are there. Okay. So, this is fx part is this, fx equal to fa naught by minus Ra, this is the fx. Okay. And x we can get this, we can plot this. Suppose you have a 2 points x naught and x1 is there corresponding fx naught and fx1 will get fx naught and fx1. So, and this is the h is the step size from this point to this point. So, this is our desired conversions up to x1 we want. So, then this shaded area under this curves we want to get. So, then fx0 x0 corresponding fx is there, x1 corresponding fx1 is this. So, then if we integrate this we have to measure that h value, fx value is known, this is fx0, fx1. So, we will put it here and put the h value, then integrating value we can get, these integrations we can get it here and put, then corresponding the shaded area we can easily find out, accurately we can find out, then the volumes we can find out. Okay. So, numerical technique is there, this is trapezoid rules. Similarly, for Simpson's rules also this is 3 points rules, here also similarly fx and corresponding x at different 3 points are there. So, 3 points will get x0, x1, x2 equals step size. So, h equals to we can find out x2 minus x0 by 2, then h value we can put it here, fx for fx1, fx2 we can know, we can put it here, and then the corresponding integrating value we can find out, and that we can put it here, then volume is required, these integrating parts we can find out. Similarly, the Simpson's 1/3 3/8 rule, 4 points rules is there also. Similarly, corresponding if we want to get within this region, so this is the 4 point rules, point 1, point 2, point 3, point 4. So, this is step 1, step 2, step 3. So, then h equals to x3 minus x0 by 3, there is 1, 2, 3, 3 steps are there. So, then we can divide it with 3, then similarly h we can find out, fx0, fx1, fx2, fx3 we can put, and then corresponding this value we can find out, and this value would be the corresponding the integrating the surface shaded area of this components. So, this is equals to the volume of the plug for reactor. This way, using either one Simpson's 1/3, 3/8 rules, 4-point rules, any ones we can choose, and we can find out the total volume is required for this type of reactors. Okay. So, now CSTR reactors, plug for reactors we can connect in series, and we can means plug for reactors with one CSTR reactor, plug for reactor another plug CSTR reactor, or CSTR reactor in series, plug for reactor in series. That way you can also connect to reduce the total volume is required for a particular conversions. That way we can also various way we can combine. So, here two different CSTR reactors. So, we have shown here CSTR reactors 1 and CSTR reactor 2 is there. So, in this case total volumes you have to find out. So, here for reactor 1, here reactant is entering and final product is coming out here. Here partially converted product will come from reactor 1, that would be enter into reactor 2. Okay. So, for this reactor 1 the design equation is this, that is the corresponding volume is this. Using these equations we can find out the volume, and for reactor 2 is the volume 2, and for that we have to use this equation, and then total volume of the system means for a specified conversions x2 is the final conversions, this is our desired conversions. Initially it was 0, and if we connect two different CSTR in series, then finally we are getting this type of conversions x2 conversion, that is our desired conversion. So, then total volume equals to volume for reactor 1 and plus volume reactor 2, if we sum up then we will get the total volume of the systems. Okay. So, here is how V2 is coming. So, here it is given material by doing the material balance for this. So, you can see it. So, Fa1 equals to this, Fa2 equals to this, and Fa1 minus Fa2, and this is the rate of generations for component 2 A at reactor 2 is this. So, by doing this material balance we can get V2. Okay. V2 equals to Fa0 x2 minus x1 by minus Ra2 for reactors 2, that is the rate. Okay. So, now graphically if we present means reactor 1 there's up to that conversions would be there means xa1, let us say this is xa1 and this is xa2, here x equal to 0. So, up to this conversions means x1 conversions will get from reactor 1, then the total volume of the reactors for reactor 1 is V1, and for reactor 2 this yellow shaded area, that is the V2. So, then total up to, if we want to get x2 conversions by combining two reactor in series, then total volume would be V1 plus V2, that using these equations we can find out. Okay. So, similarly also CSTR reactors 2 if we connect in series, that way we can get the total volume. So, let us say here we have used two reactors in series, instead of two reactors if we get the same conversions by using one CSTR reactor instead of two. So, then we can compare the volumes of two reactors giving advantage or same volume higher volume of one CSTR reactor. Okay. CSTR 1 reactors or CSTR 2 means two reactors connected in series, or instead of one CSTR a bigger size of reactors we can use. So, where we will get advantage. So, it has been observed that two CSTR in series if we connect, smaller volume is the volume is required that would be smaller than a single CSTR to achieve the same conversion. So, two smaller CSTR if we connect in series, there is some advantage of using that to get the same conversions. Okay. So, therefore, always we will choose for two smaller reactor connected in series, there will get higher conversions, or to achieve the same conversions volume is required smaller. So, similarly, in number of plug for reactors if we connect in series, there is no advantage, means if we connect once PFR in series, PFR in bigger PFR and PFR in multiple number of PFR in series. So, it does not affect. Okay. So, means whether we are using once PFR in series PFR reactors or multiple PFR in series. So, in both the cases means we have fixed that conversions, then the conversions for the desired conversion, the total volume should be the same. In case of the PFR there is no advantage, but in case of the a number of equal size C star in connected in series, then the total required volume will be less than a single C star to achieve the same conversion. If conversion is the fixed, then if we multiple number of C star is connected instead of one C star is there. So, this is much more advantage than this to achieve same conversions. Okay. So, this type of reactors means we should recommend to use multiple reactors in series. So, here see, here 5 C star was connected in series and 1 C star if we connect the same, here 1 C star and here 5 C star, here we are getting 80% conversion, here also 80% conversion, but total volume V C star of 1 reactor, V C star for 5 reactor, this is the 5 reactors. So, to achieve the 80% conversions, the volume should be different. So, here in this case and this one reactor. So, here one reactors always require the volumes of the reactor system volume would be always not equal. So, here means one reactors if one bigger size of reactors we have to use to achieve the same conversions. So, here 5 C star smaller C star if you count the sum of the total volume, always you can see that here the volume is less than a single C star volume. So, this using the 5 C star in series, that is there is advantageous than as compared to the a single bigger or larger size of C star use. Okay. Similarly, in case of the plug 4 reactors also, if we achieve the same conversion, but see here this type of means where is the advantage of using a number of smaller C star in series. Here see here the total volume was this, here see here the volume is this for reactor 1, reactor 2, reactor 3, reactor 4, reactor 5. That way total if we consider, so here it would behave like a means C star almost if we use the 5 C star in series and if we use 1 PFR. So, then almost similar means amount similar volume of size volume to achieve the same conversions would be the required. Okay. So, means this 5 C star when we are connected in series, then it would behave almost like a plug 4 reactors. So, we have studied that or we have discussed that a PFR reactors always require smaller volume to achieve a same conversions if we use a C star. So, C star always required higher volume. So, how we can reduce that volume? So, we have to choose multiple C star in series, we have to connect that way we can reduce the total volume is required for a specified conversions. Okay. So, now means C stars if this type of connection means series connection also we can do, means 2 C stars in series with that 1 plug 4 reactors also we can use. In that case the total volume we can sum up that V 1 from these reactors and V 2 from these reactors and V 3 for corresponding plug 4 reactors. So, this way we can means put it here and total volumes we can collect we can calculate, and if we use this graphically. So, graphically it would be like this if we plot it. So, F A naught by minus R A and conversions if we are plotting. So, then graphically this is for one C star reactor, this is for second C star reactors. Okay. And this is the for third PFR reactor that was connected in series. So, this is the for plug 4 reactor. So, here you can see that the total means volume, this is for V 1 volume, V 2 and this is for V 3. So, total volume this way we can measure or we can calculate. Okay. Similarly, means the 2 C stars we have connected series with a plug 4 reactor. Similarly, for a particular reactions we can connect plug 4 reactors and C star either this way or this way, means first PFR C star will come then PFR, or first PFR will come then C star, this way also we can rearrange. So, we can see which one would be the advantageous, means first C star reactors put and then C star these plug 4 reactors if we put, which one is better, where we get higher conversion, here or here. So, we have to do it by trial and error method. So, we can calculate that let us say here volume is fixed, here volume is fixed, here volume is also fixed. ठीक है. So, total volume for these combinations we can find out V1 plus V2, and these combinations also we can find out V1 V2. So, here we can check where conversions at this particular way of arrangement or combinations. So, what would be the conversions here, what would be the conversions here, both the cases volume are the same. So, here maybe if here we get let us say 80% conversion, if here we get 85% conversions, same arrangements. So, then we can say that here we are getting 85% conversion, here we are getting 80% conversion, then we should put first PFR then CSTR. If we get here higher conversions, then we should go for this way of arrangements. Okay. So, this is the way we can decide whether we should first put a CSTR and then a PFR, or a first PFR then a CSTR. This way we have to do a trial and error to get a solution to measure the actual reactor volume that is required. Okay. So, today is up to this. So, next day we will discuss something else. Thank you.